Welcome to the class. Today we are going to discuss about Lagrange's theorem in group theory. Lagrange's theorem statement says that if G is a finite group and H is a subgroup of G, then prove that order of H is a divisor of order of G. Before going to prove this theorem, we need to know some basic concepts. That is the definition of a right coset. If G is a group and H is a subgroup of G, then for every A belongs to G, we can take a right coset. The set HA is equal to set of all HA, small h into A, where A is fixed, which varies from the set capital H. Then this set is called a right coset of H in G. For better understanding this definition, here we are going to take an example that G is equal to 1, comma minus 1, comma I, comma minus I. The set is called fourth roots of unity, and with the elements of fourth roots of unity, with respect to the binary operation multiplication, G clearly forms a group. And also consider H is equal to 1, comma minus 1. And this H clearly forms a subgroup of G. So corresponding to this group G and subgroup H, for every element of G, we can define a right coset of H in G as follows. H into 1, where 1 is an element of G. H into 1 is the set containing elements of the form small h into 1, where small h belongs to H. And this set contains 1 into 1 minus 1 into 1. Here 1 is fixed, and first one is the element of capital H, minus 1 is element of capital H. So all elements of capital H, here we are considering, and the set gives the result 1, comma minus 1. So the right coset H1 containing the elements 1, comma minus 1. Similarly, for the remaining elements of G also we can define a right coset, which are H into minus 1 containing the elements minus 1, comma 1, H into I, set containing the elements I, comma minus I, H into minus I containing the elements minus I, comma I. So these four are the all possible right cosets of H in G. So for every element of G, for all four elements of G corresponding to the subgroup H of G, we can define all possible right cosets of H in G. And from this example, we can observe some points, some results, which we are using in the following theorem, Lagrange's theorem, that are any two right cosets of H in G are either identical or disjoint. Observe this example. If we consider H into 1 and H into minus 1, HA, HB. So these two right cosets are same. That means these two right cosets are identical. And if we consider H1, HI, then these two right cosets are disjoint. The right coset H1 containing 1, comma minus 1 and the right coset HI containing I, comma minus I. So both are disjoint. So that we can state here any two right cosets of H in G are either identical or disjoint. The another result is, since H is equal to H into E, we can write with the identity element H representation as HE. HE is again H, which can be considered as a right coset of H in G. And we know that from the previous results, there is a one-to-one correspondence between any two right cosets of H in G. So here we have a property that is, every right coset of H in G has order of H number of elements. That means H into E is one right coset, and all other remaining right cosets have the number of elements same as in H because of the one-to-one correspondence. The another result we can follow from the above verification, our G can be expressed as the disjoint union of right cosets of H in G. That is, if we observe from the above example, H into 1, comma H into I, are considered as the disjoint right corsets. Or you can take h into minus 1 and h into minus I are also disjoint right corsets. Our G can be expressed as the union of h1 and hi, which will give the set 1, minus 1, I, minus I, which is again the group G. So, corresponding to the disjoint right corsets of H in G, our G can be expressed as the union of the disjoint right corsets. Now coming to the proof of Lagrange's theorem. Again observe that G is a finite group. Given that G is a finite group, means number of elements in G is finite and H is a subgroup of G. Then we have to prove the number of elements in H divides the number of elements in G. That is, order of H is a divisor of order of G. Coming to the proof of this theorem. G is a finite group, H is a subgroup of G. Our claim is to prove that order of H is a divisor of order of G. Here we are going to suppose that HA1, HA2, and so on HA2 are the only distinct right corsets of H in G. That means, by using some basic result, we already know that any two right corsets of H in G are either identical or disjoint. As above, we already said that any two right corsets of H in G are either identical or disjoint. So that here we are considering HA1, HA2, so on, HAK are the only disjoint right corsets of H in G. And corresponding to these disjoint right corsets of H in G, our G can also be expressed as the union of all these distinct right corsets of H in G. That can be represented as here. G is equal to HA1 union, HA2 union, so on, union, HA2, which is the disjoint union of the right corsets of H in G. If we consider order on both sides, then we are going to decide about the number of elements in G. Order of G means number of elements in G is equal to order of HA1 means number of elements in HA1 plus number of elements in HA2, so on, number of elements in HA2. And from the another point of the above, we already said that there is a one-to-one correspondence between any two right corsets. So the number of elements in HA1 is equal to the number of elements in the right corset HE, which is nothing but H. So the number of elements in HA1 is equal to number of elements in H because of the one-to-one correspondence between any two right corsets. Similarly, the number of elements in HA2 is equal to number of elements in H. And number of elements in HAK is also equal to number of elements in H. And this sum of order of H runs over 2 times. K into order of H. Therefore, order of G is obtained as K into order of H. It means that order of H divides order of G. That means order of H is a divisor of order of G. Using the definition of it divides, when a number divides the number, another number, then that another number can be expressed as the order of H into K. Hence, order of H is a divisor of order of G. It's the proof of Lagrange's theorem. Thank you.